That split second of smooth shifting is one of the most satisfying experiences a modern bicycle has to offer. But if you take a closer look at your cassette, you'll notice it seems to be covered in wear and tear, specifically chamfers on the teeth and strange indentations carved into the sides. You might even see some teeth that look twisted or sit further back. But don't worry, this isn't a quality issue or actual wear. On the contrary, it represents the most brilliant engineering on the entire cassette. Today, using 3D animation, we're going to deconstruct this mechanical miracle. Before we get into the wear and tear, we first need to look at this regular alignment. The master spline on the cogs ensures that each one locks into a precise relative angle when installed on the free hub body. But why is this necessary? To answer that, we first need to understand the thing driving the cassette, the chain. The standard pitch for modern bicycle chains is 12.7 millimeters, or half an inch. This dimension applies to both the inner links and the outer links. However, this fixed pitch creates a challenge. Since gears of different diameters naturally have different tooth counts, timing is everything. When the derailleur pushes the chain sideways to transition from a smaller cog to a larger one, a specific tooth valley on the large cog must align with the chain roller. If it doesn't mesh correctly, the chain won't catch, and the gear shift will fail. To solve this, we have to adjust the angle between the cogs. This is done so that a specific valley on the large cog is perfectly timed to catch the roller of the chain as it's pushed over. This is the core reason why we need to lock the relative angle of every cog, resulting in that specific patterned arrangement we see. When we push the chain towards a larger cog, the chain has to wait for an entry point on that cog to rotate into position. This is exactly why you sometimes feel a delay when shifting. Now, although our simplified model shows just one entry point per cog, on real-world cassettes, engineers design 2, 3, or even more of these points to drastically reduce that waiting time. During the climb to a larger cog, as the chain is pushed over, collisions are inevitable while waiting for the entry point. The chamfers prevent the tooth tips from riding on top of the links. We'll see later how these same chamfers are just as important when dropping the chain to a smaller cog. As the shift point rotates into position, we need to guarantee that the teeth following it will mesh with the chain. These specially engineered grooves, known as shift ramps, allow the angled chain to move closer to the larger cog. Furthermore, if you look closely, you'll notice that the teeth immediately following the shift ramp look different. They are twisted or positioned closer to the smaller cogs. We call these shifting teeth. Although the shift ramp gives the chain space to sit closer to the large cog, the chain itself is still approaching at an angle. To ensure the chain can be successfully caught by the large cog, the first tooth after the shift ramp is designed to be twisted. When the first tooth corresponds to an outer link, the chain is easily caught by this twisted tooth. This is thanks to the larger internal space of the outer link and the chamfers on the inner side of the plates. The second and third teeth that follow are designed to sit closer to the smaller cog. This positioning ensures that more chain links can easily engage with the large cog. When the twisted tooth corresponds to an inner link, the internal space is much tighter. Even if the twisted tooth cannot engage with it, its angled design still helps guide the chain into the correct tilted posture, allowing the second and third teeth to catch the chain instead. Driven by the continued rotation and the traction from the shifting teeth, the chain momentarily bridges the gap between the two cogs. As this section of the chain rotates to the very top, the entire climbing process is finally complete. Unlike the climb, dropping the chain seems much simpler, more direct, and faster. Remember those chamfers on the cogs we mentioned earlier? To shift from a large cog to a smaller one, the derailleur pulls the chain outward. When the chain hits the chamfers on the current cog, the links lose their grip and stop engaging. As more links disengage, the chain suddenly snaps down onto the smaller cog, completing the shift. To achieve smooth shifting, modern cassettes are significantly more intricate than the simplified model shown today. If you found this video informative and helpful, please give it a thumbs up and subscribe for more content like this. Let me know in the comments if you have any questions.